Hello, and welcome back to Research Methodologies. Today we're going to be talking about the research foundation. And with that, I mean the journey of research. What are the steps you have to take to get research going? We'll also be looking at the language of research, the rationale behind it, its validity, and how we finally conceptualize it. So today is a bit more theoretical, and then with the hope that you can get started on the more practical side soon. So let's have a look at the roadmap of research. If we travel in our world of research, you usually start traveling on it because there is some sort of problem. Now, as engineers we are often trained, there's a problem, go fix it. As a researcher, we have a slightly wider perspective. The fix is not the necessity of the outcome. The outcome that we're looking for are valid conclusions based on the research done. That may be that there is no fix, which is a whole different outlook than the design assignments that you've often done before. So, we have a problem of some sort. In order to understand the problem, we need to study the area that has a problem. But we can never study the entire area. What we tend to do is we take a piece of it. Taking a piece of that area is what we call sampling. And then, from that sample, we want to measure something. But we have to first think of it, what is it we want to measure and how we want to measure. So for that we need a research design. So not the design of a contraption, but more a design of the research. What is it that we need to do to measure what we want to know? And then once we've made our research design and we've created our measurements, we have to analyze the outcomes. And then from the analysis of the outcomes, we have to draw our conclusions. And from those conclusions, we may find a fix, or we may find that what we found is not a fix at all. I'd like to stress here that no is a very acceptable outcome of any research. If you have a research question that says, can this be done, yes or no, and you find that given the circumstances that you were studying and the data that you have, the answer is no, that is also a very valid outcome of your research. It may not be as satisfying, because of course we all want to find something that says yes, and look, we found the fix for something, because that tends to be how we are wired. But finding out that something isn't possible and that we may have to look in another direction is equally valuable to the world of science and the world of research. So how we get there is the topic of today. So let's have a look at these steps on our research journey. Typically we have a problem, some very generic problem that's often too broad for one study, and very often also too broad for one master's thesis. So what you need to do is, when you get described such a problem, is to distill it into something much smaller and eventually to a research question and a mission statement. The ways of doing that will be discussed in week 2, but for now it's important to realize that the problem is always way too big. So once you've decided what the part of the problem is that you're studying, is then you have to look at what is the population that you're studying. So for instance, when we're talking about, say, materials, if you're going to study the strength of a certain type of composite fiber, and you want to test this practically, then you're going to have to take a sample of all the composites. Because it doesn't take a rocket scientist to imagine that you can't possibly sample all the carbon fiber in the world. So what you do is you take a unit, a selection of composites that you believe are representative for what you want to study. And by studying that sample, that is representative enough that you can then generalize it for the whole of the, in our case, composites thing that you wanted to know. So, as a whole, it's very important that you choose the right sample. At the same time, and we'll discuss this also in a later stages, to get that sample, it may not always be straightforward. Sometimes you have to make do with what you get. And whether or not that is acceptable will be discussed next week. Now let's have a look at the measure. When you are testing your sample, you're measuring something. So what you are doing is you're observing. It's a process of observing and recording these observations. What is it that you need to know as part of your research journey? Now, knowing what you want to measure then allows you to make the research design. And the research design really is the glue that holds your project together. What was it that I set out to do? How am I going to measure? What am I going to measure? and what is the outcomes that are coming out of there. Now, once you've done that, eventually you get data out of there. Now, data is always raw data, and raw data at some point needs preparing. Now, this is often seen by newspapers and conspiracy theorists as data fudging or data bending, but raw data cannot be analyzed straight away. You need to do something with it. You need to code it so it fits into a computer system. You need to make sure it fits within the realms of the mathematical model that you use it for, etc. Important things are is that you describe that clearly and how to get there. And then you stay away from terms like data fudging, tricks, etc. Although perfectly acceptable as trade talk, the rest of the world thinks you are defrauding the lot. So that is not what you're trying to do. So you have your data, you prepare your data, and then you do descriptive statistics, curve fitting, all these other things to see if your model fits your expectations. What does the data show? And then the next time is that you look at, okay, so what have I got? What is the third step? What more can I make the data? Is there significant data? And with significant, I don't mean very large. With significant, I mean statistically significant. If you've tested something in the lab and the theory tests show the theory shows a difference, you would like to see, is there a statistical difference between the two? Or for instance, you've carried out two measurements of aluminium, one from aluminium manufacturing, one other from aluminium manufacturer 2. Which one, is there a statistical difference or not? So always be very careful with significance and differences. Are you just talking difference I'm observing, or are we talking about statistical difference? And significance should really only be used in a statistical way. You do this so you can test if your research hypothesis of your research design actually holds. So that is why you analyze it. The nice thing of having a research hypothesis, and I'll come back to that later as well, is that it limits the amount of analysis you've done. Because you'll see that you get addicted to data. You always get much more data than you actually need. And it's so tempting to do much more with that. But for the research that you set out to do within your research design, you sometimes have to limit yourself. And then finally, when you've done all your analysis, you have to come to conclusions. And in the conclusions, you look at the answer to your research questions and the implication of your study. What is the impact of your study? What does your study mean for the research question you answered, the problem you were studying? You also mention what is still out there as remaining problems. These are what I call the part that you put in your recommendation section. The part where the next master or PhD student can continue to study on. And what are the limitations of your study? How controlled were the conditions? And is it a problem if those conditions aren't as controlled when somebody else does it? This is also a bit of academic reproducibility. Is your work only for your study, or can it be generalized to a larger population? And if it's limited, under which condition is it limited and why? So, let's talk a little bit more about the language of research. There are different types of studies, and basically what happens in these studies is they become we zoom in further and further as we go along. The most simple form of study is a descriptive study. Basically, you document what is going on or what exists. For instance, the proportions of votes between two parties, the number of manufacturers of aluminium, the number of simulation software available. In relational studies, you go a step further. What you start doing is you start investigating the relationship between two or more variables. For instance, is there a relation between gender and voter proportions? Is there a relation between the aluminium manufacturer and the strength or the composition of the aluminium? And then the next one, once you've found the relationship, let's see what type of relationship it is. And that's what we call causal studies. And they're designed to determine whether one or more variables cause or affect the outcome of one or more of the outcome variables, e.g. a causal effect of the advertising campaign on voting patterns. There is a very substantial difference between relational studies and causal studies, and yet it is the most violated form that we see in research. And I'll come to that in a bit more detail later. So let's first zoom in on the variables. A variable is any entity that can take on different values. For instance, age. It has different values for different people. But it doesn't always have to be quantitative or numerical. For instance, people can be left-handed or right-handed, but we can still represent this by numbers, by saying, if left-handed, I equals 1, if right-handed, I equals 2. Now, what I've done here is attach an attribute to a variable. So an attribute is basically a specific variable on a variable, e.g. left-handed or right-handed, 1 or 2, or give a rating from 1 to 5 from strongly disagree, disagree, neutral, agree to strongly agree. This is what you often see in questionnaires and is often known as a Likert scale. Now, that's the attributes. But if you look at variables in your research, you have to identify two types of variables. The independent variable, which is what you or nature manipulates, while the dependent variable is the one which you presume to be affected. So for instance, if I frown, does the weather change? Does it start to rain? So frowning is then the independent variable, and the dependent variable is the weather. Is it sunny, raining, etc. So when you define variables, which is of course a very silly example, they should be exhaustive. They should include all possible answers when you attribute them. But they should also be mutually exclusive. They shouldn't be able to happen simultaneously. People should, for instance, be very clear in which box to check if you do a questionnaire. So let's go back to our example of left-handed or right-handed. That is effectively not an exhaustive list of attributes, because some people use both hands. They're omnidextrous. So if you were to do this on a questionnaire, 1 would be left-handed, 2 would be right-handed, and 3 would be omnidextrous. And then you have been exhaustive. And you're still mutually exclusive, because one cannot be just left-handed or just right-handed or left-handed and omnidextrous, because then you haven't chosen the full set. So that is very important in any research design. This is of course a very silly example, but on a more serious level, every time you try to select things, and especially when you're designing computer code and you're defining your variables in that, you have to make sure that it's very clear which choices you make where, and that you document how these choices and these attributes are made. This so that other people who want to look at your code or understand how you come to your answers can see which choices you made and why. So I said I'd come back to the types of relationships. A relationship is actually nothing more than there is a correspondence between two variables. They somehow depend on each other. But there are two things to look for. You can look for the nature of the relationship or the pattern of it. Starting with the nature of the relationship, you can have a correlational relationship. That means that you found that attribute of a variable 1 is somehow related to variable 2. However, and this is where you get to the chicken and the egg problem, you don't know in a correlational relationship who affects who. The only thing you know is that there's a relation. If you want to know whether or not something, if you can find out what causes what, then you're talking about a causal relationship. And then you can say, well, because people got inoculated, less people got ill. That is a causal relationship. But the problem is, and this is where the press often misinterprets papers, is they read a correlational relationship and they make it a causal relationship. And whether that is true, that remains to be seen. The proof for a causal relationship is much stronger and much higher than the proof for a correlational relationship. Let me give you an example of how that can be different. And that's what we call a third variable problem. There was once a study that said that when the number of storks increased, the number of babies also increased. And that you could argue with that the number of storks increased, so the number of babies increased, so storks must bring babies. Now hopefully you're all now of an age that somebody explained the principles of the birds and the bees to you, and that you know that that isn't true. However, this is a classic example of a third variable problem. When zooming in further, the investigators found that there was a third underlying variable that caused both the increase in the number of storks and the increase in the number of babies. Now, where the wording is a causal relationship, you have to be able to prove beyond, well, even beyond reasonable doubt is more a judicial term, but beyond any statistical doubt. Because otherwise, all you've proven is a correlational relationship. And be aware that if you find some sort of relationship that seems strange to you, that there might be a third variable problem. Now, the second thing when we look at relationships is that we can actually look at the pattern of it. Now, let's have a look at the different ones in the picture here. Basically, you can say there is no relationships, there's a positive, a negative, and for instance, in this case, a curvilinear relationship. Now, none basically means that how does stuff affect this? Does your GPA have any effect on your lifetime? No, it doesn't. So that just remains what it is. There is absolutely no relationship between two variables. This can be good if you're trying to investigate if there is a relationship. This can be not good if that was what you were hoping to base all your research on, and then you may have to start again and look at your research questions and wondering if you've asked the right questions. We all more or less know the positive relationships. We've seen those a lot in simple graphs at school, but this, for instance, the longer you stay in school, there's a salary expectation that goes up higher. Vice versa, the negative relationship, for instance, that the higher your self-esteem is, the least likely you are to be paranoid, and vice versa. And the higher your paranoid is, the least likely you feel that people take you serious. That's what we call a negative relationship. And then the one that's most likely to find in most of our problems is some sort of curvilinear relationship. In this case, it's about the severity of the illness and the dosage level of the medication. If you have a severe illness and you take medication, at some point you'll start feeling better and better and better. But there's an optimum in that, because if you take too much medication, the side effects might actually make you feel ill again and your illness gets worse again. Now, in this case, it looks like a parabola, but whether it is one, we don't know. What you see is you get data, and then you can start making assumptions on curve fitting and other things to see if the data can be mathematically predicted. Those are patterns you can study. But you always have to be very careful that all the data points that you find are real and true and not an accident. And so whether you're measuring a one-off or whether you're measuring something that is really the case also depends on your research design. And again, on the sample and on the reliability of the measurements that you do. And we'll also discuss the reliability of measurements in week 2. So let's have a look at hypothesis. A hypothesis is basically a specific statement of prediction. It describes more or less in concrete, rather than theoretical terms, what you expect to happen in your study. For instance, going back on the frowning, and is when I frown, it starts raining. So that means that my alternative hypothesis describes the prediction, while the null hypothesis describes all other possible outcomes with respect to the hypothesis relationship. So, if I don't frown, it doesn't rain. So these hypotheses should be mutually exclusive, but exhaust all possible outcomes. And in order to test a hypothesis, you must be tested in such a way that one hypothesis is accepted and the other is rejected. The hypothetical deductive model theory to confirmation. I will try that again. Probably not. It's not going to sound any better. But by the looks of it, the sun is shining behind me, so I'll frown. No, it's not raining. Not the right hypothesis, rejected. So, let me come to data. Now, we will talk about data extensively as well over the next few weeks, but in a very simple form is you have quantitative data. That is numbers. We like numbers, we can add them up, we can multiply them, we can put them in computers, etc. But we also have lots of qualitative data. Scientific literature to read, text therefore, photographs, film, all sorts of other things that we can study. But beware, all qualitative data is based on quantitative judgment. Is it good or bad? And all qualitative data can also be summarized and manipulated numerically. For instance, if we take out a photograph, we could go back to the colors and determine the RGB value of each pixel in each photograph. Actually, we can start by dividing a photograph into pixels. We're already numericating it there. So it's very easy to do that, and qualitative and quantitative tend to go hand in hand. It's just which decision you make on how to quantify what in where. So let's have a little bit look about the why of the research, the rationale of it. So if you look at the structure of research, it's like an hourglass. We begin with some very broad questions, we tend to narrow down, we focus in, we operationalize. That means we finally get to actually do some measurements. We observe, we have data, we analyze data. From that data we reach conclusions, and then we generalize back to the research questions that we have, the big broad questions that were there earlier as well. So basically that sort of gives you the components of research. We have a problem, and from the problem there's a question, and that question is then linked to the theory testing. There's a program that calls the calls. We have units with which we measure, and there come out the outcomes, the effect. And totally that forms the design. So we have a problem, there's a question we like to answer, there's a program, what's the cause? Well, we have units that we get through that, and we measure the outcomes from the effect it has on the variables, and from that we get design. Now, when we start to do all this, we have to reason things, and this is where it gets a little bit more philosophical. We start talking about deduction and induction. And what we do is, in deductive reasoning, we move from the more general to the more specific. And in inductive reasoning, we move from specific observations to broader generalizations and theories. Sherlock Holmes being the most famous one for his inductive reasoning. So, in deductive reasoning, the more general things are, when people tend to have a cold, they tend to have a runny nose, feel dizzy, look poorly, and sneeze. So when you come to your GP because you're not feeling very well, he deductively reasons down from all the more general things to one more specific thing caused to make a diagnosis. In inductive reasoning, you go the other way around. This is what your mother does. Ooh. You sniff. You may have a cold. Yeah, actually, I have a cold too. Oh, we both went to visit Aunt Sally over the weekend, and her children had a cold. So really, those we must have been infected, etc., etc., etc. It becomes bigger and bigger and bigger. One single thing gets blown up into a whole generic thing. If you find this more difficult to see, go watch any TV detective. Most of them are very much about inductive reasoning, about who killed who with the candlestick in the cellar, etc. So let's have a little look at deductive and inductive reasoning in a more graphical display. For deductive reasoning, we look at the theory, there's a hypothesis, we observe, and then we confirm that our theory is right. In inductive reasoning, there's an observation. From the observation, we start looking at a pattern. Then we make a tentative hypothesis. This person must have done it. So that is then our theory, he's guilty. So the way it goes the other way around. Both are valid forms of reasoning, and both have different ways of doing research. So to a certain extent, deductive and inductive reasoning are both a philosophical way that you can help you get to the answers that you're looking for. Now, the next thing we have to discuss is the validity of research. So how do we define validity? Validity is really about the quality of the various conclusions you might reach on your research project, and to a certain extent, the best available approximation to the truth of a given proposition, inference, or conclusion. That may sound again like data fudging to some of you. However, the truth is not a black and white thing, as much as we'd like to say that it is. What is true for one person may not be true for another person, and the same goes for research conclusions. What is true for your project may not be true for a similar project, but just slightly different. So what you're trying to do is to best describe reality or the best based on your findings. However, what we know to be real or to be true will change from time to time to time. So how do we get the best possible validity for your research? Well, then we have to look at the two realms involved into research. If you look in the realms of research, you have the land of theory and the land of observation. In the land of theory is what the cause is believed to be, me frowning, and the effect identified means it rains outside, affecting something and measuring in it. In the land of observation is observing of these effects happen when we test the hypothesis. So when I frowned, did you see the weather change to rain? That's the difference when you look at those two things. And in order to get to from the land of theory to the land of observation, we need to operationalize. And operationalization, now there's a squirrel word, is the act of translating something more theoretical into its manifestation, taking the idea and describe it as a series of operations and procedures in which we test or write a computer code or simulate, put in whichever part it is. I realize that for some of you may think, well, this all looks very social sciences bit, perhaps because the examples are the easiest to make. But if you look critically at your own research, it also goes for your research. Making sure that you know what's in your land of theory and in your land of observations, and how you get from one to the other, and how you describe that in most detail, will actually enhance the quality of your work greatly. So if we look at these realms and components of research, so what you see is there's a theory, and in the theories you have the cause construct, what do you think causes it, and what do you think will happen. And then you have to operationalize it so that you basically create that event. And then you see, so that's what we call what you do, what we test, and what then comes out of it. And then we can see if what we think happened actually happens. And that's basically how the world of the land of theory is linked to the land of observation. So how does that then work in our validity? Now, basically, validity types are about, it's like a staircase. The first easy one was, is there a relationship? So, when I frown, does it rain? The next term, is there a type of relationship? Curvilinear, causal, etc. Then we have to look at the construct validity, and that is there a link between those relationships that we observe? We find something in our observations, and how does that compare to the theory that is out there? Is that linked? Do our tests confirm the theory or reject the theory, and if so, why? And then the next thing is the external validity, and that's probably the highest type of validity you can read. Can we then generalize these findings in relationship to a much bigger population than the one we studied? Is there much further use? And basically, the better the research, the higher the validity is. Although I have to say, with some of it, it's also a case of luck. Because some research topics will, for now, in the stage that they're in the world of science, not get past internal validity or construct validity. Although I would expect that most of the thesis work should really contain some sort of construct validity. You really should go past the high school science project, or is there a link between two variables. You should also look at what the theory does and ground it in theory. So for me, personally, when you're doing your work, ensure that you reach at least construct validity level. And for external validity, that really depends on the type of research. Now, and if you look at this again and we talk about the land of observation and the land of theory, then the first two are of course firmly only in the land of observation. And that is what I mean, that I believe those to be lower level validities, and I think you should actually go for construct validity at least, because then you're also linking it into the land of theory, which is more or less what you should be doing at academic level. So, let's have another look at a different way of looking at research. If we look at the theory, this part of Introduction into Research, And the research problem formulation, I have a problem that I want to fix and this is what I'm going to research, they're like a yin and a yang. Part of you can't wait to get on with it, and part of you knows that they have to do all the paperwork first, or aka make sure that the research design is in the right possible way so that you do not get into a problem later on. So, keeping an eye out on external validity, construct validity, internal validity and conclusion validity whilst you're sorting out your research versus all the sampling and measurements, your research design and the analysis you're doing is a very important thing to do for any research. If you tend to go head over heels into the let's go measure, sample, etc., you'll probably find you get into real problems in validating your research and you may not even get past more than a conclusion validity, which would be an extreme shame because basically you have some data which you've analyzed and there's a conclusion. Whereas if you look how these two each are linked, if your design is right, you might actually say a little bit more about the internal validity. Is there a causal relationship? If your measurement is right, you can even say, okay, well, I've measured it based on this and this theory. I can say something about theory. And if you sampled it right, aka your sample is representative enough to make a much more generic statement, then your external validity goes up. So basically, the truth of the matter is that if you are in the bottom part of things and you don't do your work, your preparation work right, you'll never get out of the purple area. And basically that means pass on your thesis rather than at least a 7 or an 8. And the way I look at it is the higher you can get up this line and you reach the blue side of sampling and external validity, so a very good sample but good external validity in the end, then you are in the cum laude area and your work is actually adding significantly, in this case in Roost, in a very wrong word, as in a large part by adding to the body of science, which is what we are trying to get you to do in your master and your PhD thesis. You're trying to do a unique new piece of work. You're trying to add knowledge that we haven't got yet to the body of knowledge of science that we are currently looking at. So, coming back to how valid it is. Conclusion validity is therefore, can we even, did we identify a relationship? Internal validity, what type of relationship? And in construct validity, if it is causal, how does the operationalization of the theoretical construct reflect the ideal? And were you able to measure what you wanted to measure? And then finally, in external validity, given the causal relationship between the constructs of cause and effect, can we now generalize this effect to other persons, other cases, other materials, other simulations, other places? You work it out. What else can we do with your work? So if you look at that as a staircase, you can see that you have to go up, and the higher up you go, the better and the more valid your research is and the more appreciated your research will be. So, this was all the theory. So how do we now conceptualize? How do we get going? Finally, you may think, all this theory. I'm sorry, there's more to come. But let's start for a little bit to give you a bit of inspiration and hopefully get you thinking, which will help you through the next part because you already have an idea in your head. So where do research ideas come from? Well, usually most research ideas, especially engineering, come because somebody's experienced some sort of practical problems and it's identified, and they basically say, help, please give me a student to fix this. It can also be that we're having a very good discussion and an idea comes up thinking, wouldn't it be good if we could look at? So in that sense, we look at what is out there. The larger questions that people have, or actually larger questions that the world has, it tends to be formulated in requests for proposals, known as RFPs, or research calls, be it regional, national, or EU or international, about worldwide problems that need addressing and the context in which it operates and how they think they should approach it and what funding they're willing to put forward to it. Because unfortunately we are getting very close to the point that free research with no funding is becoming less and less likely. I'd like it to be different, but this is the firm and harsh truth. Because research costs money and somebody needs to pay the bill. So when you're looking for the ideas, have a look in those things. Also be mindful that you can never solve everything in its entirety. You will probably only solve a tiny little puzzle piece in a 2,000 piece puzzle. So Then we come to the point of feasibility. Is the research idea feasible? See, many of us are blessed with great brains. We tend to have all these great ideas, and some of them are really good, and some of them, after 10 more minutes of thinking, you go, no, actually, that's not going to work, or that has already been done, etc. So you always have to check if your research idea is feasible. And don't be disappointed, out of the 20, 30 ideas you'll have, maybe only 1 or 2 are feasible. But the good news is you only need 1. Then you need to look at feasibility in terms of how much time are you willing to put into it. A thesis project plus literature study cannot last 5 years. It's as simple as that. There are restrictions to these things. So what is the trade-off between that and what you are practically willing to do? And then there's also the trade-off between what's available within the institute that you're doing your research in. If you want to do research in a wind tunnel on speeds that we do not have here, then yeah, it's a great desire. So unless you find a university willing to take you on for that project, you're stuck. You may have to adjust your ideas of what you want to do. Other practicalities is, of course, can it be done? Should it be done? Ethical considerations. Can we get the cooperation to get it done? Is there, for instance, also a supervisor here with the right knowledge to supervise you? Because you may have a great idea in a field that within this faculty or this university, there is nobody who knows anything about it. Which in the learning situation that you're in would be extremely unfair for you to do this. We cannot supervise you properly, and most importantly, we can also not assess you properly. Because we have, to a certain extent, on that area, no idea if what you're saying and claiming and measuring actually is any good, already exists, etc. So that is also something there. And furthermore, are the required costs manageable? We will not buy you a whole new research building just for you to do your master's research. I'm very sorry, but I hope you understand. Now, one of the ways to look at feasibility, the most important one I think you need to look at is, has it already been done? Many people have great research ideas and then they simply Google it, and you Google it, I often mean Google Scholar, and they go, oh, that was done 5 years ago there, and they found it couldn't be done. Now don't despair, it's worthwhile reading through it why it couldn't be done, and if you can think you do it better, that's always better, disproving somebody else's research, only you better make sure you do it right. Or you see, oh yeah, that was exactly what I wanted to do, no, that's not a good one. So basically a literature review is when you start looking at what is already out there, what has already been done, and within the problem that we have, is it worthwhile, how do I see if where I fit in, what is still left to study to a certain extent. And also it is a way of finding methods that have been done to measure. If you want to measure something similar to what's been measured before, that will actually get your measurement setup arranged, or the theoretical model that they've used that you may be able to extend to fit your work. All those sort of things is what you find in a literature review. So when you start this course and start on your thesis a problem definition, it's also important that you do a literature review to see where does my research fit in. It's important there, however, that you concentrate your efforts on the most credible scientific literature. This is why Information Literacy 3 has been included in this course, because that teaches you a lot about how to identify literature and to see if it's actually worthwhile. There's a Dutch saying that says, paper is patient, meaning anybody idiot can publish anything. That already used to be the case in print. I imagine what it's like now in the world of the internet, where a new truth is put online every minute. So make sure that you know how to identify credible scientific literature and back up the claims that you have, and also to do this as early as possible. If you're in for a longer term research project and it is a fast moving field, however, do keep an eye on your literature. You wouldn't be the first one whose research was overtaken by somebody else publishing exactly the same work you're researching just before you graduate. Now, in a master's thesis, that's not the end of the world, but you do really look good if you can actually compare. It's also nice to have a bit of benchmarking, and hey, maybe you can find a flaw in their work. Probably not, but hey. But also to see if you're on a longer research project, to see if you need to review where you're going and maybe change direction as to make sure that your work is still a unique way to work. But literature review is not something you can leave to the final end in any of the work that you do. It forms the basis, often the theoretical basis and the conceptual basis of why you're doing it and how you are doing it. So what do I look for? Typically you look for studies that are quite similar to your anticipated study, and the nice thing is they also did a literature review. So in there you can see a lot more papers. So it's like a snowball approach. You get more and more and more literature. Having said that, be careful, because some of the anticipated, some of the studies that are similar to your anticipated study might be quite old. And although some research was definitely done in the 60s and 70s that couldn't continue for lack of computational power, lack of facilities and all the other things that we do have now, many, many, many years later, that doesn't mean that you can use it one-on-one. You may have to look for additional discoveries since. Is the theory that, for instance, they're referring and basing their study on still accepted as the current truth, so to speak? Or has the theory also been modified over the years? The nice thing about looking at other people's research is that it actually helps you capture all the major relevant constructs in your approach to your study. What have they done? Why have they done this? Hey, that seems to be the way to go. Why do I do this? How does that work for my studies? To a certain extent, it is a legitimate, providing you reference it nicely, a form of copy and improve. It also helps you in finding and selecting appropriate measurement instruments and approaches, and also to not do the approaches that they failed at. So that is what I mean, that no is also an answer. For every no that you find, somebody else in the future won't have to do that and will not find no, because they don't have to do what you've done already. So other people have published no's too, so make sure you find them. It avoids you all the pitfalls and it saves you from reinventing the wheel, which more importantly saves you time and leaves more time for you to do that great scientific discovery that you're hopefully setting out to make. So, what is the summary of today? Well, we talked about the language of research. We talked about variables, the attributes, causal relationships, hypothesis, and the units of analysis. We also talked about the rationale or logic of research and how it's structured, which components are there. We talked about deductive and inductive reasoning and about the validity, and that the higher the validity, the better your research will be valued. In our terms, we have validity defined by its conclusion, internal construct, or external nature, with external being the highest one you can reach. And we also talked a little bit more about how research is thought of or conceptualized. So, what's next? Well, continue with the next section of this online course, and hopefully you'll start thinking about how you are going to structure your research problem, and try and keep up, because that means that you don't have to do so much work when the deadline approaches. Until next time, for now, bye-bye.